detail that Ioana noticed. If you remember, when we discussed the potential of the first segment, we said it's this height, which is Q1, sinus Q1, okay? And then this segment, we said it's, we said it's L1 L1 sinus Q1 plus L2 over 2 sinus Q2. Right, that's what we said about this height here. Okay. The truth is that the way I wrote Q2 here, it's like this, but basically Q2 is defined as this angle. That's why we're confused. So it's just this part. Okay? And this angle is, if this is like this and these two are parallel, this is basically Q1. So more correct is if this is Q1 plus Q2. Okay? Because Q2 is defined by this extension, basically, not vertical to this. I corrected it on the slides as well. And it's already online. And we continue with our discussion. So this is what we were left at, the total kinetic energy. Now we have the total kinetic and the total potential, and we can use the Lagrangian to do the derivations as Lagrange defined them, together with the help of Euler, and to define the final equation of motion for our system. Now we will do some, again, tricks and some tidying up. First of all, just focus on the top part. The kinetic energy we can write in a much more clean format, like this. So instead of having to write all the time all these things, we'll just use this thing and write it as matrix D. What is the dimensions of D? It's n by n, where n is the number of joints we have in our system. So for a 2-joint system, D will be a 2 by 2. It will always be a square matrix with the size of the dimension of our system, and the potential will be the sum of the heights and the masses multiplied together. G can go out, so we have something like this. Okay. Now here I wrote D depending on Q. You remember why? Because these things here depend on Q, the position of the joints. The transformation matrices depend on the position of the joints, and the Jacobians. Okay? We'll see that this is important. Alright. The total Lagrangian will be this thing in a very condensed form. And we know how to calculate D, we know how to calculate these all things. Okay? Another way to write this is like this. Now, here what do? I take each term of this matrix D. It's basically, when I have equations with matrices inside, let's say this equation, D, Q, D. Let's just focus on this part, okay? Let's call this M. Okay? T. This is basically a system of equations, another way to write it. Right? What system of equations? Let's say this is a 2 by 2. and D has elements D small, 1, 1, D, 1, 2, D, 2, 1, D, 2, 2. And Q has Q1, Q2. Okay, so in the end this is Q1 dot, Q2 dot, because this is transposed, D11, D12, D21, D22, Q1 dot, Q2 dot. Okay, I can write this. If I do the multiplications, I will end up with what dimension? So this is what times 2, 2 times 2, 2 times 1. I will end up with a 1 by 1. But yeah, it's basically this sum, right? Where I and j is the columns and the rows of these things. Okay, so let's take just one term. So it will be this times this, Q1 dot D11 plus, so this times this will be a 1 by 2, so this will be, plus Q2 dot D21, this will be the first element, and the second element will be Q1 dot D, I ran out of chalk, D12 plus Q2 dot times D21, Q1 dot Q2 dot. Okay, so if I do this multiplication, I end up with this vector here, and this remains. And if I do this multiplication as well, I will have eventually, I'll write it quickly, so this will be multiplied by Q1, so this will be Q1 square, Q1 Q2 plus Q1 Q2 times Q2 square. Okay, which if I write it with indices, it will be this part here. So when I and j is 1, for instance, it will be D11 times Q1, which is this part. Right? When I is 1 and j is 2, this will be D12 Q1, Q2, which is this part. When I is 2, j is 1, it is this part. And when I and j is 2, it's this part. Okay, and then you see it's summed together, all of them. Okay, so this is just another way to write the same thing in expanded form. We will see why is this useful. So now that I have this Lagrangian written like this, I can write the equation of motion using the rule that Lagrange and Euler came up with together with the derivations we saw last week. Let's see it in the next slide to remember. Sorry. So if you remember, this is the way they defined it. If you remember last week here we had y in the example, and here y dot and y. Basically there we put the generalized coordinates. If I had expressed my system in x and y, then here I would have had x and y. Okay? Now I have expressed my system in the coordinates of q1, q2, or q and q dot. So here I need to derive based on these coordinates. And that's where the usefulness of the Lagrangian comes, that I can choose whatever coordinates I want and write the equation of motion based on those coordinates. And in the case of a robot, it's very convenient because we can use the coordinates, the joint coordinates. Okay? Now, this will result in a system of equations. And I will have one equation for each joint. for each coordinate, to be more specifically. But because we have coordinates equals to joint coordinates, then it will be the same as the joints. Okay. So I need to do this derivation for each element of Q, which is what we have here. Okay. So I need to derive with Q1 and Q1 dot, with Q2, Q2 dot, Q3, Q3 dot, and so far and so forth. Okay. Now I'll remind you very briefly what these things mean. If I have the Lagrangian, what do? I derive the Lagrangian partially. Let's do this a bit more accurate with, let's say, Q1 dot. And the result of this, I do derive it over time. Okay. Minus the partial derivative of the Lagrangian with Q1, let's say. Okay, and this will give me the torque or the input force in that coordinate. Of course, this can be 2, 2, 2, 3, 3, 3. That's why there I write kappa for specific coordinate. Now, let's start seeing what are these terms. Let's see again how our Lagrangian looks like. So this is how our Lagrangian looks like. Okay? And let's start with this term here. How can I calculate this term with this Lagrangian? I need to derive this Lagrangian with my Q dot, let's say, kappa. Which terms from here do they depend on my Q dot kappa? Does this term depend on Q dot? No. So the derivative with Q dot will be 0, right? And here, what do I have? Which of these terms, let's say this kappa, let's take it to be 1 for now, just to prove the point. Okay? Which of these terms depend on Q1? I'll write them again, just to be Q1 dot D11 was square plus Q1 Q2 Q1 Q1 Q2 dot D12 plus Q1 Q2 D21 plus Q2 square D22. That's how these terms were. Okay. So if I want to derive with a Q dot 1, which terms will they go away and which ones they will stay, and what will be the result? Does this depend on Q1 dot? This term? Yes? Okay. And remember that this was 1 over 2 outside Q, right? So what's the derivative of this with Q1 dot? 2Q1 dot D11. Okay. Here, does this depend on Q1 dot? Yes. What's the derivative with respect to Q1 dot? Louder. Q2 dot times D12. And here, same, plus Q2 dot D21, and this term, 0. Okay. Good. What did I do wrong? Sorry? Yeah, it was squared, but anyway, it does not depend. So it is still 0, right? Good. So this, in the end, it will be Q1 D11. Basically, that's something I did not really explain, but with this matrix D, these elements contain terms, but the non-diagonal elements, they do not contain terms, basically. Or maybe they do. Let's think that they do now, okay? But they have the same value, D22. So these two are equal. They're usually 0 as well, but for now we'll just take it equal. So D11 and D21, they're equal. So this gives me plus 2Q2 dot D12, let's say. Okay, and with the 2 here, it goes away. So in the end, I have this thing, right? If these two are the same, which they are. So in the end, this first part, I can write, so this thing is the sum for, there I have it with k, here I have it with 1, so it's the sum over j, which is the number of joins, of d k j q j dot. So it is, if k is 1, it is the sum of, in our example, of d1j, q dot j, where j is 1 until n, or in our case, it will be 2 joins. So from j equals to 1 until 2. So q1 times d11 plus q2 times d12. Okay? And what do I need to do with this thing according to the first equation? So I just calculated this part. What do I do here? I derive with time. What is the derivative of this with time? Do this term depend on time? The elements of matrix D, we said that they only depend on Q. So they don't depend on time. Okay? So this means that only this term depends on time. Okay? So I need to derive just this term. With time, this means that it will get one extra dot. Yep. Yeah, unless actually these depend on time as well. That's my mistake. Yeah. So correction that this also might depend on time. So then when I do this derivative, I have to take this term, j equals to 1 until n, d I j q j dot dot. So I derive this part plus the derivative of this part. J equals to 1 until n d1j with time times qj dot, which is what we have here. Okay, so I derive in parts. The derivative of this with time, it's the derivative of q times this, and the derivative of q dot times this, and the derivative of this times q dot. Okay, so that's why I get the 2 dots here, and then I have the derivative of this over time, or another way to write it is like this. Why does this depend on time? Basically because q depends on time. And if you remember, let's say that I have dij which depends on q, and q depends on time. So I have basically this thing. If I take the derivative of this with time, it is the derivative of this with, the derivative of this with q, and the derivative times the derivative of q with time. So this is d. You remember derivation rules. If I have a function which is a function of another property and I want to derive with that property, I need to take the derivative of the function with the second function and then the derivative of the second function over time in this case. So this is how we go from this side where I need a derivative of dkj over time, but dkj depends on q, which depends on time. That's why here I get this part here, because the derivative with q over time is this term. Okay? Cut and cut. You have to remember a bit the derivation rules. Me too. So this part here is our first term of the equation of motion. We did that by deriving the Lagrangian over the velocity of the generalized coordinate and then deriving this over time. Okay? Any questions so far? By the way, I have too many d's here. Yeah. This is the d from the derivative, this is the d from the element of the matrix there, which depends on q, which depends on time. Do you remember this rule? Like, if I have an f which is a g of t, the derivative of f of g of t with time is equal to the derivative of f with g times the derivative of g with time. You remember this? Derivation rules? So this is what we're doing here. With instead of f and g, we have d and q, and time is still time. Any questions? Okay. Now let's move on to the next term. So we calculated this term, the first term. Let's calculate this. What is the derivative of the Lagrangian just with the joint coordinates, not the velocities? Let's remember how the Lagrangian looked like. So here I want to derive this L with Q. Which terms depend on Q? Does this term depend on Q? Yes, so I need to derive it. Does this term depend on Q? As well, so I need to derive this as well. So how do we do this? Basically, this term, if I derive it with Q, it will be, let's write the sums as well, ij, and it will be, just these terms depend on Q, just the dij, q, because these are not depending on q. So it will be the derivative of dij with q, qi qj dot, right? And here minus j minus g, sum from I equals to 1 until n, the derivative of this h of q with q. I should do the right question once. Times mi. Okay, or yeah, the potential, just potential. This is the potential. This is basically the derivative of the potential with q, what I have here. Okay. So here I have a term which depends on q1 and q2, qi, qj dot dot, and here I also had a term depending on qi and qj dot dot, qi dot qj dot basically. Okay, when I combine the two together, the terms from this side and from this side, we put them together. There is a minus in this equation, that's why this term gets a minus. Okay, the minus here becomes plus, and overall my equation of motion will have this form. Okay, this is for k, for a specific value of k, which k runs from 1 until n, the number of joints. So in the end I will have a system of equations, one for each joint, which shows me kind of the dynamics of that joint. Now, if this is a system of equation, I can write it in a general form like this. As you see here, I have some terms with q dot dot, so second derivative of q, where this is basically the joint acceleration, how fast the joint accelerates over time. I have some terms that depend on q dot, so just velocities of the joints, and I have some term here, depends on the design of the robot, we might have depending on q, or we might not depend on q. Usually we will have some dependence on q. So I can write it like this. I have a term that depends on the acceleration of the joints, I have a term that depends on the velocities of the joints, and I have a term that just depends on the position of the joints. Okay? Now this you could somehow relate to Newton's equation in a way. For Newton's equation we saw that it was m times acceleration equals to force, where acceleration is the second derivative of position. Okay? Have you seen systems with spring and dampers? Have you seen such systems? Where you have a mass, you have a spring, and you have a damper? Have you seen? Do you remember what was the equation for these systems? And let's say I have a force as well. What was the equation of motion for this system? It was something relating to acceleration and mass, something relating to velocity, and something relating to position. Okay, where k is the spring coefficient here, c is the damping coefficient, and m is the mass. Now, if you see, this equation has the same form. It has some terms that depend on acceleration, like this. It has some terms that depend on velocity, and it has some terms that depend on position. And all these things are equal to a generalized force or a torque in our case. So if we relate with this equation, what do we expect this matrix D to contain? Things related to the mass and the inertia of the system, right? You remember what this D was? This was this n by n matrix that we saw. And it had all the terms, m1, m2, the moments of inertia, everything was in there. Let's have a look. It was basically this term here, where it contains the mass, contains the moments of inertia, and how these things move. So this matrix D is about the inertia of the system. Okay, the same way as this mass is about the inertia of the system. Now this is a bit more complicated than just moving in one direction, because again we have the rotations and we have more than just one mass. Okay? C, so stuff relating to velocity. Here we have the damping coefficient. Okay? So in our case, you could see there's a damping. We didn't include any dampers and so on, but it's other effects related to centrifugal forces and Coriolis terms. That's how we call them. Okay? It's the dynamics of the system that have to do with the speed of the joints, the velocities of the joints. While the term G contains just the dependence on the potential, so things relating to position. Okay? In our case, we saw potential depends only on gravity. So that's why you also use the letter G. It really depends on, it has to show, how gravity affects the dynamics of our system. Okay? Yeah. This is so you get a bit of a feeling and intuition about what these terms actually do. Now, I jumped from here to here. You see that I wrote this C as basically these terms here. Just to make it more clear what the C is basically these terms. Don't need to know them by heart, but just for completeness of the story. The elements of matrix C, the elements Kj, are these sums here, which also kind of relate to, as you see here, I have elements of D, also relate to masses and inertia to some extent. But how they affect the velocity of the system. So what can I do using this equation? What is my input for this equation? And what is my output? If I know what is the position, the velocity, and the acceleration of my joints, what can I calculate? The torque that resulted in this motion, the torque at the joints. Is this what I want? What do I want? The acceleration of the end effector, right? So I want the inverse dynamics. So this is the dynamic model, and what we always want is the inverse. Oops. So how do I go from here to an inverse problem? Any ideas? I need basically to have as an input position and velocities and torques in order to calculate what the resulting acceleration would be. Yeah, so I write T tau minus C Q dot minus G Q, and we multiply from the left with a D minus 1, and this will be equal to Q dot dot. Simple. Simpler than inverse kinematics. Okay? This should be something we can do, inverse, and then I just need to do some minuses here. And we'll see how we can use both of these equations in order to do control of the position and of the velocity of the robot in next lab. In next course and next lab. Next lab. Okay? Any questions? We'll try to apply this on the robot and find specific values. You will do this in the next laboratory. Well, actually you already did for the 1 degree of freedom, now you'll do for the 2. I think we give you the matrix actually, right? Yeah, so we give you this matrix, so we will just do some kind of simulations using these two equations. Any questions? It's a long path. In the end, what's important is to understand that this matrix here, it's easy to calculate, right? We saw it's just that thing with the Jacobians and the moments of inertia and the masses, right? So you calculate it once for the robot and it's there. And if it's a two-joint robot, it's a 2x2 matrix, not too many terms. Okay? We saw that this C matrix is also easy to calculate if we know the matrix. Okay? And this G is also relatively easy. If I have the potential, I just need to derive with the joint values, Q1, Q2, and so on. And I have it. Okay? So, it might seem like a complicated thing, but I just want to present you, okay, how do we go from this equation and the kinetic and the potential energy in order to reach this equation, which is relatively easy to calculate, okay? It's good if you see like how, what's the path to reach this thing. And understand and get a feeling about what these terms are. So when you actually try to control the robot, you know if something goes wrong or something doesn't behave, you can have an intuition like, okay, probably it seems that the mass is too big, or then I have to check again how did I make the matrix D, and so on and so forth. Okay? If you understand this part, then you can immediately do this calculation. You don't have to do all this long way that we took, but it's good that you saw it, I hope. So, no questions?